Okay, today we are going to be looking at some recent examples of magnetic circular dichroism, or MCD, which is an absorption spectroscopy utilizing the Faraday effect to induce optical activity in all species, not just chiral molecules. And it's pretty much a measurement of the difference in absorption between left and right circularly polarized light when a sample is in a magnetic field parallel to a light beam. So, for a little bit of history on MCD, it was in the 1840s that Michael Faraday discovered that light and electromagnetism are related when he passed a beam of light through a medium in the direction of the magnetic field, and the angle of polarization of the light was rotated slightly, which you can see at the end with that beta angle there. Due to birefringence of light polarized in different directions, which gave rise to the term magnetic optical rotation, which is how in the 1930s we ended up looking at how this rotation was found to be wavelength dependent, which they coined magnetic optical rotary dispersion. And this eventually led to MCD as a spectroscopic technique 30 years later. And there's two important reviews were published by Buckingham and Stevens was the first one, and Schatz and McCaffrey, and they're really the first ones to highlight some beginning uses of MCD. And ever since then, MCD has primarily been used to determine the electronic states involved in transitions that are observed when degenerate electronic states of the molecule being studied are split in the presence of the applied field. So we will look at a couple of recent examples that do just that. So here we have kind of a very, very general MCD spectrometer setup. And so on the left, we have a CD spectrometer, natural circular dichroism. It utilizes the same change in absorption, but it's only observed in chiral molecules due to the requirement of an environment that naturally has helical handedness. So we start with the CD spectrometer on our left. They normally have some kind of linearly polarized light source that is passed through a modulating device to transform the light into circularly polarized light. So that's our RCP and LCP, so our right circularly polarized and left circularly polarized light, and it just kind of swaps between them. And as the light changes directions, the absorption will change as well. And then we can pass the light through our sample, which is in the magnet. So our magnetic field is actually going to be parallel to our light arrows drawn, and the transmittance is then recorded by our detector. Some pretty important parameters essentially for MCD is our Rockoff parameters, A, B, and C. And these are not observed in all MCD spectroscopy, but they can be used to explain a lot of MCD spectroscopy, and I will explain what I mean. So in this figure, we have on the left a ground state A and an excited state J with no field applied. And on the right, we have three different terms, A, B, and C, with field applied. And we'll talk about what each of those mean. So our first Faraday term, the A term, is caused by the Zeeman effect, which means that degenerate electronic states are split in the presence of a magnetic field. So this is telling us that previously these excited states J were degenerate, and now they're being split into kind of like J1 and J2. And we can look at the difference between our ground state to the first excited state versus to the next excited state there. Our B term has to do with field-induced mixing of different excited states. So in that figure here, we see two different excited states, J and K, but they end up being so close together with the applied field that we get some mixing between them, and we can measure that as well. And we'll see an example of that soon. And with our C term, it is the splitting of a degenerate ground state because of the field, the magnetic field. So A splits into two different states, and again, similar to A, we can measure the difference there as we go to our excited state. So our first recent example is from a 2024 paper by Hattori and others, and they were looking at magnetic circular dichroism studies of these luminescent triaryl methyl radicals. They'd seen some cool absorption and emission properties previously, but they wanted to study them further, and it was suggested to do MCD. And so they proposed MCD of these racemic mixtures of these radicals at room temperature. So this is the MCD spectra they got for a couple of these molecules. But as with most MCD spectra, our goal was kind of to assign the transitions we were seeing here. And so in order to do that, they needed to do some DFT calculations to calculate the molecular orbitals and energy levels of these excited states. So that's what we can see on the right here. So using these DFT calculations, the authors were able to contribute that strong UV absorption bands seen in our figure on the left bottom to a couple of different transitions, first of all being D0 to D8 and D0 to D9. And they could even further characterize them as the alpha HOMO to the alpha LUMO and alpha LUMO +1. And as I said previously, the A, B, and C Faraday terms come to be relevant when we're looking at MCD spectra. In this molecule, only the B term is involved due to the non-degeneracy of this molecule, right? So we don't have a degenerate ground state, and we don't really have a degenerate excited state. So we only have the B term to look at. And one of these excited states, D8 and D9, are close enough in energy to allow mixing. So that was our definition of our B term earlier. They were able to use DFT calculations to calculate the B term of the electronic transition as expected, and they were very large, indicating that there's a lot of mixing between these two excited states. So as we can see on this next figure here, our vertical lines represent our B terms. So we're looking at the B terms of two different molecules we discussed here. And we can see that they definitely have differing intensities of B terms, signifying that the molecule on our left has much stronger mixing of their excited states than the molecule on the right. So this study as a whole pretty much gave us a way to study CD without separating enantiomers or using something expensive like chiral stationary phase HPLC. So in our next example is a 2020 paper where they were looking at these tetrakis thiodiazyl porphyrazine metal complexes, and they wanted, of course, to do MCD spectroscopy of them to study their electronic structure. And on the right here, we can see one of these MCD spectra on the top paired with its UV vis spectra on the bottom. And from that UV vis spectra, it kind of tells us where to look. So that really strong, intense peak around 650 nanometers is called our Q band. And the MCD signal related to their Q band is related to energy splitting between the two HOMO and energy splitting between the two LUMO. So we were able to get that information from our UV vis and then use DFT calculations to compare to our MCD spectra to characterize the HOMO and LUMO here. To finish out our conversation about Faraday terms, it's important to note here that this molecule discussed in this recent example 2 does not have C term, but it does have A and B term. The lack of C term can be attributed to a lack of degenerate ground states in both recent examples. So that applies to our last slide and this slide as well. And recent example 2 has degenerate excited states that split in the presence of magnetic field, giving us our A term, and mixing of excited states, which gives our B term, as we discussed in the last example. So kind of in conclusion, both of these recent examples kind of wanted a better understanding of complexes' electronic structure, and they used MCD to do so. This is often paired with DFT calculations to find molecular orbitals of the complex before comparing that with MCD to assign specific transitions. And these are my references, and that concludes my presentation.